Welcome back, everybody. Before anybody picture, there we go. Okay. Before anybody has like a question, so the exams, I do have them graded. I just haven't entered them yet. I decided for two main reasons. One is that I have one more student who needs to do a makeup, and two, I realized that if I give it to you today, then it's if I give it to you today, give it back today, then it would be due on Monday, right? And that wouldn't allow you to over the weekend take some time and think about it and then come to questions with me on Tuesday during my office hours, or email me during the weekend when you're probably going to be trying to work on it most of the time. So I figured it would be better to give it to you on Wednesday, so you have until Wednesday to get it back to me. So that is the reason why you're not getting back today. Part one is the fact that there's a student who still needs to do a makeup, and then part two is that I want to give you the an adequate amount of time to digest and learn from your mistakes. Okay, but make no mistake, they will be posted on what's called probably later today or tomorrow. And if you've gone to our Canvas gradebook, you'll see that it has original exam score and then exam score. So it's like original exam one score and exam one score. The exam one score is the thing you're actually going to be like, that's actually going to appear in your grade book. So right now, well, once it's posted, you'll see it in both columns to show you what your score is currently and give you an accurate representation of your grade, but knowing fully well that you can get half the points that you missed back. So once you turn in the redo, if you decide to do so, that original exam score will stay the same, but that's worth 0% of your grade, because it's just to show you what the original thing is, and for my own reference to look at my students' performances and see the improvements and things like that, and see if my policy is doing what it's supposed to do. So any questions on that before we get started? Okay, so then we left off last time talking about the definition of the derivative, which was the limit as h approaches 0 of y of f of x plus h minus f of x all over h. And we learned the key fact number one back here is that you are not finished computing the derivative by the definition, at least. You're not computing, you haven't computed it yet unless you have canceled the h in the denominator, because we've talked about that with limits. Is the problem, like, you need to get rid of the problem, and this is a problem. If you have h in the denominator, that's going to be dividing by 0, and that's a problem. So you need to cancel that h by some type of algebra. Some way, somehow, it has to happen. So just like with everything we've done, algebra is key here. So whether it means simplification and canceling and then factoring, or finding common denominators and then factoring, or as we saw here, we didn't finish it by doing conjugation, multiplying by the conjugates thing. So we'll finish this one up real quick. This becomes the limit as h approaches 0 of 3x plus 3h minus 4 minus 3x minus 4, all divided by h times the square root of 3x plus 3h plus or minus 4 plus the square root of 3x minus 4. And I'm not going to distribute the h in the denominator, because at the end of the day, what I want to do is cancel that h. So factoring, like foiling it in, wouldn't do anything for me. I'd have to factor out again. So that's why I'm not going to foil it in or whatever. Any questions on the algebra they got here? Remember, the reason why it's like why the square roots are gone is because we're multiplying by the conjugates, which basically squares the two terms and takes the difference. Not basically, it does that exactly. So you got 3x plus 3h minus 4 minus 3x minus 4. When you distribute that minus sign in, that's going to end up canceling the 3x's and the minus 4's. Does everyone see why? It's important to know why, because it's like you're going to need to do that algebra. So it's going to be 3x minus 3x, and then -4 minus a -4. So -4 plus 4, those cancel. We end up with this, the limit as h approaches 0 of 3h, all divided by h times the square root of 3x plus 3h minus 4 plus the square root of 3x minus 4. And then just so happens that the h's cancel. And since we're running out of space, I'm just going to plug in I'm going to evaluate the limit right now. So drop the limit side, plug in h equals 0, and get this. Color equals 3 divided by the square root of 3x plus 0 minus 4 plus the square root of 3x minus 4. And I would like this to be simplified just a smidgen, just a tiny bit. And ideally, yes, we wrote a chain of equalities, so we don't have to, but it just looks neater if you write dy dx or y prime, either way is fine, is equal to 3 over. Notice that that's 2 of the same thing in the denominator. That's 2 radicals of the same thing. So those are like radicals, so they can be combined to write this as 2 square root 3x minus 4. And that is our derivative. Any questions on that? Okay. So at this point, we have computed 1, 2, 3 derivatives. I want you to observe these are functions, right? Here, like in this first one, f of x, the original function, is a quadratic function. And the derivative is a linear function. It's a function. That's the important thing. The derivative is a function. So you plug in a value, you get back a value. But what that value can represent is very, very important, as we saw in the picture. If you look at a specific a value, if you look at a specific value, like we had in this definition right here, you look at a specific value, then graphically, it represents the slope of the line tangent to the curve at that point. So that is the key fact number 2, is that for any a value, f prime of a is the slope of the line tangent to f of x at x equals a. So when you as it stands, let's write that down. I'm getting ahead of myself. Just because this is such a cool concept. Up until this point in your mathematical career, if you think about it, everything we've told you, every function that we talked about, in Math 126 in particular, it's like, this is a function. Yeah, it's a function. That's all we know about it. I'm going to give you random functions and tell you what their graphs look like, and that's about it. Here are the properties of this function. Why? Why are we studying those things? Because now that we have calculus, we can actually find a use for those things. So, in particular, now when we find the derivative, we can think about it as both a function, but if you plug in specific values to your into your derivative, you get slopes of tangent lines, which sadly we don't get into it too much in this course. In Math 182, you will talk about Taylor polynomials, which basically tells you, which is fascinating, is that every function that you know about, pretty much every function that you've experienced, can be approximated by derivatives. So you can keep taking derivatives, and eventually you will get the function pretty accurately. Like we're talking within 0.0001. You'll get there. And when we talk about differentials in section 3.6, you'll see another application. But That's kind of cool, in my opinion. This is the first time we've actually seen an interpretation of a function other than just as here's the function, here are its properties. So this is the way I like to do these things. So for f of x equals 3x squared plus 1, find f prime of 1 by the definition, then find the equation of the tangent line to f at x equals 1. So you could do this in two different ways. When we were trying to find f prime of 1, that will be the slope of the line tangent at x equals 1. You could first find f prime of x and then plug in 1. That is an option. But since it's not asking us to find the full function, we're adding on an extra step. So instead, what we'll do is we'll find f prime of 1, which by definition, so all it is, it's the definition of the derivative, but instead of being f prime of x, it's f prime of 1. So all the x's get replaced with 1s. So this is the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. All it is, the original definition of the derivative right here. I mean, it's y, but the same thing. Y of x plus h minus y of x over h. The only thing that's changed is the x's have been replaced with an actual finite value. So let's find out what those things are off in the side note land. F of 1 plus h is 3 times 1 plus h quantity squared plus 1. Which, just to save us on time, I encourage you to go through the algebra if you don't see how it came to be, but that will be 3 plus 6h plus 3h squared plus 1. Or if we simplify it, right, yeah, 4 plus 6h plus 3h squared. And then f of 1. By the way, while we're computing, this will equal 3 times 1 squared plus 1, which is equal to 4. A couple things I want to mention about why I'm doing what I'm doing. To talk about the reason why I'm being so particular with my verbiage and everything like that, because there's a problem here. There's a problem that arises, which is confusing to read if you're not very, very careful. It takes time to get to this point. As a mathematician myself, I'm always looking for this, and I need you guys to be looking for this. So the reason why I like Leibniz's notation so much is because look at my key fact number 2. If you're skim reading that, you might not see that it says f prime of a. And you might just read that as f. Or if you're not writing carefully enough, if you're kind of writing quickly, you might not see that as f prime. You might accidentally write like that or something like that. And then you can't tell that it's the f prime. And so your notes are confusing to you because it's saying that f of a is the slope of the line tangent to f. That wouldn't make any sense. It's confusing. So if I said dy dx evaluated at a, that would be a different thing. So that's the reason why I like Leibniz's notation. And that's why when I'm computing the function, I'm making sure to write f of 1 and then writing out what f of 1 is, even if you could compute it in your head, which you should when you get quick at it. But this is reminding me, this is being plugged into the function, not the derivative, So just to keep in mind, because it can be confusing at first. You start, like, as you get better and better, you don't need to look at that as much. I have no idea. There's something useful. I'm certain, but like kind of addictive. But okay. So let's continue now. Now that we have f of 1 plus h and f of 1 and h, we can go like this. This is the limit as h approaches 0 of 4 plus 6h plus 3h squared minus 4 divided by h, which then nicely for us, the 4's cancel. we get the limit as h approaches 0 of 6h plus 3h squared, all divided by h. And please remember, you cannot just cancel, like, I'm going to draw it for a second, just so that we know what not to do. I'm writing it in big red here. We cannot do that, remember? Because in one context, in the denominator, it's a factor. H is a factor in the denominator, but it's a term in the numerator. You cannot cancel factors and terms together. You can only cancel factors together. So what we have to do, it's not all that bad. This has a common factor of h, like that. And you could say, well, Phil, why didn't you factor out the 3 as well? Nothing wrong with that. You can. It's not wrong to do so. It's just, I only really want to cancel out the h. That's why I'm doing it that way. But it's not wrong to factor out the 3 as well. That's not wrong to do so, but just kind of making you do extra work. And just to save on space, so the h is gone. So key fact 1 has been satisfied. We have canceled the h in the denominator, which was the problem. So now we can plug in the limit. We can evaluate the limit, drop the limit sign, plug in h equals 0. You get 6 plus 3 times 0, which is 6. What did we just do? Well, we just found the slope of the tangent line at x equals 1. So this is m sub tan. And then I'm going to put underneath it at x equals 1. So m sub tan meaning the slope of the tangent line. That's what I usually write it. And the reason for that is sometimes you will be looking at multiple slopes, which you'll see in another question in a second. You want your m tan, like I say m tan to say this is specifically the slope of the tangent line. Okay. Any questions on that? Did that answer the question? No. The question was asking for the equation of the tangent line, not just the slope, but the equation. Now, do you remember the two different forms? This is another side note land topic, which is the two forms of a line. A line equation. There's the slope intercept, which everyone's all goody-goody about. Ooh, it's the slope intercept form. Oh, we're so cool. I disagree. I think the slope intercept form is way less good. You guys remember point slope form? Yeah, point slope form, best form. And I'll explain why in a second. So point slope form is y minus y sub 1 equals m times x minus x sub 1. Those are the two forms. Whenever I ask you a question about writing a tangent line, you can use either. I will not require you to do one or the other. However, I will recommend to you that the point slope form is far better. For a number of reasons as a student. One, as long as you got the point and the slope, you're done. You're done. You don't even need to do any more work, which is awesome. That's done like that. Whereas with slope intercept form, you'll have to find b, unless by some miracle, the point in question is the y-intercept, which doesn't happen very often. So slope intercept form is going to take more work. That being said, I will say this with regards to that. If you need to use the tangent line, then slope intercept is better. So if you're being asked to do something with the slope of the like to do something with the tangent line, write in slope intercept form. And that's going to be kind of a common thing. My recommend, like when it comes to finding derivatives, as we'll see soon, Basically, don't simplify unless you need to use it for something. Same thing here. Point slope form is just the unsimplified version. You can like this is what when I teach 126, I talk about the connection here. You can go from point slope form to slope intercept form very quickly. Distribute the m, add the y sub 1, you're done. You've got point slope form. Whereas going from slope intercept to point slope form, much more difficult, much more algebra intensive and being very clever. So if you need to use something that we're dealing with in this course, simplify, i.e. go from point slope form to slope intercept form. If you're not asked to simplify, if you're not asked to use it, keep it in its unsimplified form. That's a good rule of thumb. So anyways, sorry to take a little side detour, but it's important because when it comes to a line, we need either, like, there are two things that you need, or like there's two options. You either need 2 points, right? In order to find the equation of a line, you need either 2 points, so you can find the slope and then find the point, or you need the slope and a point. We have already found the slope on the left. We still need a point. We still need a point. All right. So how do I find it? Let's reread the key fact number 2 for just a moment. For any a value, f prime of a is the slope of the line tangent to f at x equals a. So this is a tangent line to the curve f, not to f prime at all, but to f. So if I'm going to find a point, I want a point on f. So on original function f, not f prime. That's a common mistake that students make, is they try and find f prime of 1, which you already did find, by the way. We already did, but in the original function. Now, sometimes in a problem statement, it will give you the point, in which case, done deal. But this one didn't. Oh no, what am I supposed to do? Nothing, cry. That was my main go-to method in grad school, was to cry. I think that's a good way to do it, to solve problems. But in all seriousness, it does help sometimes. It's a point on the curve. So we have the x value 1. All we need to find is f of 1. That would be the y value, right? Function values and y values are synonymous. So that is to find f of 1 is 3 times 1 squared plus 1, which is 4, which gives us the point 1, 4. Now, yes, we already computed it in Brown, but just so we see how the process. We took an x value, we got back a corresponding function value or a y value. That gives us our point. So now we have a slope and a point, and we're all done. So y minus y sub 1, y minus 4 is equal to m, 6, times x minus x sub 1, which is 1. Or if you want to be that person, you could write this as y equals 6x minus 6 plus 4, so minus 2. I will accept if there's a question on the upcoming exam. Wow, for now, it's not upcoming. That's a lie. It's not upcoming. We got a couple more weeks. Or on a quiz or whatever. You can leave it in either form. I can guarantee you I will never ask you to write your derivative in a certain form, or your tangent line in a certain form. Whatever you're more comfortable with is fine with me. And I'll explain why, though, another reason why I like point slope form in a second. Any questions on that? Okay. Next problem. The derivative of y equals x cubed minus 2x plus 5 is y prime equals 3x squared minus 2. We can do, like, I'm just giving that to us so that we won't have to go through and compute it all over again. You saw how long those problems take. So I'm just going to give us the derivative. Determine the equation of the line tangent to the curve at the point 2, 9. Just as a small note, notice that if you plug in 2 into y, 2 cubed is 8 minus 2 times 2, that's minus 4. So it's 4 plus 5, that's 9. It's a point on the curve, on the original function y, not on y prime. So if you're going to determine the equation of a tangent line, the first thing you need is a slope or 2 points, right? So slope, what we're going to do is we're going to find y prime of 2. That's the x value. That's the x value of the point that we're trying to find the tangent line at. So y prime of 2 is equal to 3 times 2 squared minus 2. That's 3 times 4, 12 minus 2, that's 10. This is our mtan. That's our slope. Found it already. Excellent. Done deal. And luckily for us, for the point, it's already given. Two comma 9. So we've already got it. That being said, we could like sometimes the problem says at x equals 2, in which case you need to do that extra little step and find the function value. So this is y minus y sub 1, so y minus 9 equals m, which is 10, times x minus x sub 1, which is 2. That's the way I would leave it, because I'm not being asked to do anything with it. And then, or you could write it as y equals 10x minus 20 plus 9, so minus 11. However you want to write it, it's your prerogative. That being said, like, and if you want to write it in slope-intercept form, you know how to, like, if you need a refresher on how to find your b value, please let me know, and I'm happy to show you. But I just prefer knowing point slope form because you can get to slope-intercept form so quickly. Cool. All right. So, example 2.1.6, the derivative of the function 1/3 x cubed minus x squared minus 7x plus 2 is f prime of x equals x squared minus 2x minus 7. Just to save us on time, could you imagine doing x plus h to the 3rd power? That's foiling it 3 times. I don't want to do that. I mean, you can, and there's some problems that do it, but God, it's annoying. Determine the points where f has a tangent line with a slope of 8. So we want the points on the curve f where the tangent line has a slope of 8. So let's interpret that. The tangent line has a slope of 8. That means we want m tan to equal 8, right? But m tan is the derivative at a specific a value. This is equal to f prime of a. So we want these two things equal. We want to solve the equation of setting the derivative equal to the slope. Does that make sense? Let me say that one more time, because this is the conceptually hard thing to grasp at first. We want the tangent line to have a slope of 8. The tangent line's slope comes from the derivative. So what we're asking to do is set the derivative equal to 8, because if we do that, we will find the x values that would make the derivative 8. So that is to say, f prime of x has to equal 8. So that's really saying x squared minus 2x minus 7 equals 8. And that is a that is a polynomial equation. The way we solve polynomial equations is bring everything to one side so that one side is 0. That way we can use the 0 product rule. So I'm going to subtract 8 from both sides and get x squared minus 2x minus 15 is equal to 0. That gives me x minus 5 times x plus 3 equals 0, which gives me x equals 5 and negative 3. John Doe student. Classic John Doe. Classic John Doe. Such a classic thing for him to do. He boxes this. This is a 10-point problem. I give them 8 out of 10. Why do I give them 8 out of 10? Because that's where the x values are, but that's not what the question is asking for. If it said find the x values, but it's saying determine the points. So John Doe student forgot to plug these in to the original function to find the points on the curve F. So to find the points, plug into F, the original function, the OG. I'm gonna be especially particular about mentioning that it's the original function at first. While we're still getting used to identifying F prime versus F, because it is a little bit wonky at first. So F of 5 with so I'll write it out 1/3 times 5 cubed minus 5 squared minus 7 times 5 plus 2, which is, off the top of my head, I do not know. So I'm going to, that's 125 over 3 minus 25 minus 35 plus 2. That is going to be negative 49 thirds. And F of negative 3 in the interest of time, that will be negative 27 over 3, negative 9, minus 9, this would be negative 9, negative 3 squared, plus 21, plus 2, which gives me 5. So we'll have 2 points. We'll have 5 comma negative 49 thirds and negative 3 comma 5. Those are our 2 points. I made sure to bring that up because I want to warn you about this. Just like with the problems that were saying, like find the points of or find the x values of discontinuity or finding intervals of continuity, how they're kind of 2 parts of the same coin. And the same thing. So you want to be reading these things carefully, making sure that you're answering the question at hand. If it just said determine the x values, we would have stopped where John Doe student stopped. If we wanted to, but this question was asking for the points. All right. Last key fact that we want to talk about is why do we care about the derivative? Why should we even care at all? What is the point of this thing? And the point, in a mathematical sense, is that key fact number 2, that it represents the slope of the tangent line. However, in a real life sense, it represents the instantaneous rate of change. So as opposed to this is how you can determine how fast you're going on the freeway. You're calculating your odometer on your dashboard. It's using calculus essentially to figure out your speed. It's taking in a roundabout way, it's taking revolutions per minute and then dividing it by thickness, all that stuff. But if you want to, you can find your instantaneous rate of change. So your average rate of change will be that secant line, taking where you started, where you finished, divide which gives you the total amount of miles, divide by the amount of time, that gives you your average speed. But if you want to know how fast you are traveling right now, that requires the derivative. And so that becomes very, very useful from a physical sense, especially if you're trying to map particles and things like that. You're trying to figure out where the particles will be. And in order to do that, sometimes you need to know how fast they're traveling. This also gets used in terms of biology. That's a big one. It's trying to find the instantaneous rate of change, how fast the population of a certain bacteria or a wolf population or whatever is changing over time, to see if it's got a positive rate of change or a negative rate of change. Those 2 things can be very, very important to an ecosystem. So We'll talk about this more later, probably at the end of section 2.2. But in physics, the position of any position of any object is usually denoted by S of t. Why? I don't know. Why didn't they use P of t for position? I don't know. But I'm not a physicist. Physicists are weird people. They call this shape, this beautiful shape, it's called a torus. And physicists call it a donut. So they're very, they're not clever. They don't want to sound smart. It's a torus. It's not a donut. Lazy. Physicists are lazy. I'm kidding. They're way better than us. They're just a better mathematician. The derivative of this function is gives us the velocity, which is denoted by v of t. So the derivative of the position is the velocity. Kind of makes sense. At one point you're here, then you travel 50 feet or something like that, and I have it over a certain amount of time. That gives me my average speed. So if I take the derivative, I'm finding the instantaneous speed, which would be velocity. And so thus what we have is that S prime of t is equal to v of t. So what this is just saying is that in order to find the velocity, we take the derivative of the position. That's what this is saying. So any questions on that? All right. So differentiability, the concept of having a derivative. We say that a function is differentiable at x equals a if f prime of a exists. For any function, we say that it is differentiable if f prime of a exists. If it exists everywhere, we would say that it's differentiable everywhere. So what does non-differentiability and differentiability look like? How do you interpret that graphically? So the most common types of points of non-differentiability are things like discontinuities. So I want you to draw three different things. So I want you to draw three little XY grids. It does not need to be perfect. The great news is I get to duplicate this. And so for all of them, I'm going to label a point like an x value A to show where it's going to be non-differentiable. So you could have something like this. And sadly, people watching the recording, you are not going to be able to see this interpretation. Please feel free to ask me to show you in class at some point if you want to see this. But I don't have my pointer doesn't do this. I'm going to draw all the pictures first. That's one such example of a discontinuity, right? That's a jump discontinuity. You could have a removable discontinuity like this. Or you could have an infinite discontinuity. Nope. And I'll tell you why. just a moment, so I'm gonna have to. I'm tall enough to reach there, but I don't want to have to straighten. Everyone's drawn that. Hopefully, can you guys all see this purple pen if I were to put it up here? Can you see that? Oh, it looks purple as well. Maybe use a different color, maybe pink. Do I have a pink pen? I have a red pen, that'll be perfect. So, so I'm saying that it is not differentiable at A. Imagine that this pencil, this pen, excuse me, the red pen is the tangent line. So, which has a slope and a point on it. Tangent line exists here because there's a tangent line. So the slope so the derivative exists there. Exists there. But over here, on one side of A, you got a positive slope, and on the other side of A, you've got a negative slope. So the left and the right hand, remember, the derivative is a limit. Limit as h approaches 0. So on one side of the limit, you've got a positive slope. On the other side, you've got a negative slope. So the left and the right hand limits do not agree, and therefore the full limit does not exist, thereby making it so that it's not differentiable. This one's a little more tricky though, the middle one, because if you were to graph it with your pen, right? Derivative exists. It's like basically flat, and then on the other side, it's kind of doing the same thing. But the problem that arises, the reason why it doesn't exist for this piece is based on the definition. So I'm going to rewrite it. You don't need to write it, but it's always good to kind of have practice. Limit as h approaches 0 of f of x, or f of a plus h rather, because we're doing a specific value, minus f of a divided by h. Do you see where the problem lies? And why the second one won't work? There's no f of a. There's an open circle there. And even though it could be the situation here, like with a solid dot above it, that would still cause a problem because you'd be trying to find a tangent line, but where you would find the slope would be using that point, but you don't have that point. You have this point, and it would be like it wouldn't work. So that's that's the reason why the derivative doesn't exist in that situation. And last but not least, I hope you can see it, like on one side you start having an infinite limit, and on the other side you have a positive. So, or like you have to jump down here. That doesn't exist there. More like in addition, f of a doesn't exist. So that part breaks apart as well. The other way you can have it is with corners or cusps. So I want you to just draw two of them here. Two graphs should be sufficient. So here, the first one I'll do corner, and a cusp. So a corner would be something like this. Whereas a cusp would be something like this. This is the A value. This is the issue. Here's A. I'm going to erase those circles for just a moment so we can look at it and understand why. Once again, with my red pen representing the tangent lines. So for this curve right here, positive slope, positive slope, positive slope. So the tangent line's existing, but at A, on one side has a positive slope, on the other side has a negative slope. So the left and the right hand limits don't agree, therefore it doesn't exist. Cusp is a little different because as you get closer and closer to the tip of the cusp, your tangent line starts having an infinite slope. The slope starts getting more and more and more positive until it's basically vertical. And then at A, it switches. So on one side, it has positive infinite slope, and on the other side, it has negative infinite slope. So those are the corners and the cusps. And then the last one where you would not exist, and this one's very hard to draw, but I only need one picture. it looks like this. Very hard to visually see. I'm going to plot the points so that I can work on making sure. This happens, one specific example of this function is the cubed root function. You see the cubed root function has this problem, but I'm going to draw a tangent line right through here. Not right there, through there originally. So that's a vertical tangent line. Which implies the slope undefined. Which implies f prime of a is undefined. Let's digest that one because that one's kind of weird. Probably the weirdest one of all these. Because this would be a situation where when you plug when you compute it, you'll get that the limit doesn't exist. But like you might have it say, like it might say that it goes to positive infinity. Like you write positive infinity, but that, remember, infinity doesn't actually exist. It's not a number, so you would say that the derivative doesn't exist. So vertical tangent lines, those are x equals, right? Vertical lines are x equals. Horizontal lines, y equals. Like y equals number, x equals number is vertical. And what we learned with vertical lines is that vertical lines have an undefined slope. And since the tangent, the derivative represents the slope of the tangent line, what you're saying is that the slope is undefined, then f prime is undefined, i.e. it doesn't exist. So, last little thing about the conceptual nature, just kind of nice, is that if f is differentiable, then f is continuous. So, the reverse is not true. The reverse is not true. That is to say, continuity does not imply differentiability. By the way, the abbreviation for continuity is CONT, and the abbreviation for differentiable is diff''bull. Diffbull. So the reverse is not true. If you're continuous, that doesn't guarantee that you have a derivative. As this problem, as the corners and the cusps suggest, this function here is continuous. You draw it and it will be continuous everywhere. But you don't have a derivative at A. So continuity doesn't imply it. And then just so what does a differentiable everywhere function look like? What does it look like? That's a great question. And the thing is, it usually looks like a nice, what we call smooth curve. So you don't need to draw this, but just so you can see it. This right here, that is a continuous and a differentiable function. Wherever I draw a tangent line, I'll have an existing slope. Once I start doing things like this, like that doesn't exist at those several little jagged points. So a differentiable function is one that is smooth and very, very flowy. Anyways, in the interest of time, maybe we'll save that for a recording or something like that. That's just going to be unnecessary for now. So I'm behind. We're going to skip to 2.1.9. So the next one says the graph of f is given below, and this was before I had the ability to add arrows. So that's that one. Like if you remember, like it's been a week, almost a week, so you might not remember the exam, but there was a graphing problem in the exam, right? almost guaranteed on every single one of my exams, there will be a graphing problem. So could have more questions than these types of things, could have less, you never know. But this one, at which points is the function discontinuous? So we're asking a question from unit 1. That's going to be finding all the points where we have infinite, jump, or removable discontinuities. So moving left to right, first discontinuity that I see is at -4, then at 2, and then at 5. And those are the only discontinuities. Only discontinuities, not non-differentiability, but non-discontinuity from discontinuities. So x equals -4, 2, and 5. Where is it not differentiable? So continuity, if you're not continuous, you're not differentiable. If you're not continuous, you've got to jump. I mean, like if we go back up here for just a moment, discontinuities imply non-differentiability. So discontinuities create different issues with differentiability. So all three of the same ones, the -4, 2, and 5 are included. And these ones, because discontinuous, but we have others. We already covered, so looking left to right, before -4, it's a very smooth curve. Very smooth curve. So there's no different, like there's no points of non-differentiability up until -4. We've already talked about -4. So that was an issue, but we've already taken care of that. Then going here, we see we have a cusp at -1. So -1, oh, whoa, wrong thing. -1, and that's because it's a cusp. We already talked about 1. We already talked about 5. And then the last one would be at 9 because there's a corner. Any questions on those? So to find non-differentiability, look for places it's discontinuous along with those cusps and those corners and potentially vertical lines, vertical tangent lines. All right, my favorite question, my favorite one. I'm going to underline these. Let's use, what colors do you guys want to use? Orange. Sounds great. We'll do that one for f prime of -7. And then f prime of 8 we'll do in brown. Wait, no, that looks too close. Let's do green. All right. F prime of -7. John Doe student looks and said, okay, well, f prime of -7, that's going to be -3. Why is John Doe student wrong? That's F. That's right. SROM is absolutely correct. That is F. How do I find f prime of -7? So we have to remember the key fact number 2. The tangent, the derivative at any given x value represents the slope of the tangent line. So if I draw the tangent line there and look at its slope, that would tell me what f prime of whatever it is. So I'll draw a tangent line at 7. So f prime of -7 is the slope of this tangent line. Therefore, since m tan equals 0, that implies that f prime of -7 equals 0. Because the slope of the tangent line, that's a horizontal tangent line. So that has a slope of 0, which means that the derivative is 0 there. Any questions on that? That is a weird concept at first. And just to get excited for you guys, this is so fun, like being able to like take a problem like this, and there's so many fun questions you can ask. Later on, when we get to unit 3, what you'll be able to ask is what is f double prime of negative of 7? What is the f double prime? If this was the graph of f prime, what is f going to be at those values? All those things can be answered later on. So very exciting stuff coming up. And then last but not least, f of 8. So here's 8. And if I were to draw a tangent line to f at 8, it ends up being the exact same line. So tangent line ends up having same slope as the curve. The curve, like f ends up being, so this is a piecewise function, in case you couldn't tell. And the tangent line actually ends up being the exact same line. Whenever you have a line, the tangent line ends up being the exact same thing, or the tangent lines are always the same line. So we just need to look at the slope of that line. Let's see here. So you can take any 2 points. I'm just going to take this one right here, up 1, 2, 3, 4 over 2. So m tan equals 4 over 2, which is equal to 2, and that will equal f prime of 8. The slope of the tangent line is the derivative at that x value. It doesn't matter which 2 points you take, just find 2 points. If it's easy to find, if it's easy to look at the graph and find the rise over the run, do that. If it's hard to find that, take 2 points and use the slope formula. However you want to do it. But regardless, if there's a problem like this and you need to find the slope of a line like that, I will make sure that the points are there. There are at least 2 nice points that you can use to figure it out. So f prime of 7, f prime of -7 is equal to 0, and f prime of 8 is equal to 2. Any questions on that? Yes.
So how do you know the tangent line ends up having the same slope as the curve?
Like that's a great question. So I'm going to draw like this is a very, very useful, like, or not useful, but interesting fact about if your curve, if your f of x function is a line, what you'll find out is that f prime of x is just equal to m. So with a linear function, your derivative is constant. And so, and in particular, it's the slope of your curve. So given any point on your curve, whenever you take a point, if you're trying to draw a tangent line, it just ends up covering over the same curve. So no matter, like, that's the cool thing about lines, is that they're the tangent line to a line is the line itself. So excellent question. I want to grab that part. Whoop, over there. Cool. Oh, Isabel. Sure. Absolutely. All right, I'd like to take a 5-minute break. Let's get up and stretch, get some air or whatever, and come back at 10:06. Let's do 6.5 minutes. So come back at 10:06. People watching the recording, please go do some yoga, whatever. All right, we're back and we're starting up 2.2. Hopefully we got through a decent amount of it. These are the basic differentiation rules. So You are still going to get hazed. Quiz on Wednesday is going to be on 2.1. And so, and as I suggested before, there might be something about the definition of the derivative on the next exam. Hint, hint, wink, wink. Maybe, just maybe there might be a question. I'm not saying that there would be, but either way. But part of mathematics is running through hazing processes. So now that we've done it the hard way, mathematicians really sat down and they said, well, that's a really cool concept, but that's really, really annoying to compute. You're telling me, like, if I ask you to find the derivative of f of x, don't write this down, but if I ask you to find f of x, the derivative of this function, not too bad, x plus h squared. What if I was asking you to find that? Do you really want to go out and FOIL x plus h 20 times? Do you want to do that? I mean, granted, you could bust out Pascal's triangle. You guys remember Pascal's triangle, right? Come on, who remembers Pascal's triangle? Or is this complete gobbledygook? Does anyone remember this? It's very, yeah, well, at least one person. Pascal, famous mathematician, he figured out a pattern, which is fascinating that this pattern ends up actually giving you all the coefficients of your terms. Very, very cool. Pascal's triangle. Feel free to look it up if you're curious. But point being is that mathematicians sat down and said, well, there's got to be faster ways to do these things. And so they figured out several rules. So the first one is the constant rule, which says, and so I want you to leave, I'm going to basically draw some dashed lines here to separate things so that I have enough space to draw an example as well. Sorry that you won't be able to do this as well, but the constant rule. ddx of c, the derivative of any constant, is 0. And ddx of ax is just a. So just like with limits, ddx is an operation. Limits are an operation on an expression, right? You take the limit of this expression, and when you finally take it, you drop the limit sign. In a similar fashion, ddx is the process of taking the derivative. So ddx is an operation on an expression. So we're saying ddx of c, that is saying the derivative with respect to x of the function c, and this is saying the derivative with respect to x of the function ax. And the reason why it's 0 for a constant function, think about it. This is a constant function, right? If I draw any tangent line, no matter where I draw it, my tangent line is the same line, and that's a slope of 0. So the tangent line represents the slope, so the slope is 0, so the derivative is equal to 0. And by a similar argument, ax is going to be just looking like this. Or it could be the other way around, right? It could be negative version, whatever. But if you draw that line and you take any derivative, as we were explaining, and I'm sorry, I'm still trying to remember names. Your name, I can't remember. Not Isabella, the person behind you. Sorry, I'm blanking on your name. You're not looking at me. You're looking at your notes. What's your name again? Aiden, that's right, Aiden. As Aiden asked earlier, the reason why it would be a is because the slope of the tangent line is just the tangent line is the exact same as the original line. So the slope is the same as the slope of the line. So a. The most important rule, the one that you will use the most out of any rule, is the power rule. So let's actually just do some examples on the side here. Example. The derivative of pi is 0. Any constant. Doesn't matter if it's a real or irrational number, an irrational number, an integer, it doesn't matter. The derivative of any constant is 0. And then another example, ddx of negative 7x is negative 7. Power rule is the most important one. What this one says is d dx of x to the n. So the derivative of x to any power is equal to n times x to the n minus 1. That is the power rule. Proving that. It's quite a doozy. And by the way, if you want to see the formal proofs of any of these things, please feel free to ask me. I'm not going to bore you to tears with it, but if you do, or if you are curious, please feel free to ask. One thing I just want to make sure that we respect about this one is that proving that for integers, i.e. that like the derivative of x squared and so on and so forth, x to the 5th, x to the 17th, not too terrible. Proving it for negative numbers, slightly more difficult. Proving it for rational numbers, slightly more difficult than that. Proving it for irrational numbers, very difficult. That is a grad school level proof. And it takes a long time and it's very annoying. But we are going to get to use it without proof. We're going to get to use this fact to give you 2 examples of this one. The quintessential example, d dx of x squared. As we start off with these things, we are just going to, we're going to go through all the motions, but I want you to get to the point where your mental math tricks are quick. So this will be 2 times x to the 2 minus 1, or 2x to the first power, which is 2x. The derivative of x squared is 2x. d dx of x to the square root 2. Yeah, it looks weird. Does, but square root 2 is a number. It's 1.41-ish. So you can still use the power rule on that. This becomes square root 2 times x to the square root 2 minus 1. Now, unlike the first one, because 2 minus 1, I can combine those and make it 1. Square root 2 and 1, they don't have, you cannot combine them without making an approximation. So you just leave it as is. You leave it as the square root of 2 times x to the square root of 2 minus 1. Because anything else would be an approximation. You could write 0.414 whatever, but that's an approximation, not the actual value. And I like things to be exact. The next one is the constant multiple rule, which says that the derivative d dx of c times f of x is equal to c times f prime of x. So meaning that you can ignore constants and just put them out front. Very nice property. We don't have to worry about finding the derivative of the constants separately. We can just put them out front, take it out, like just worry about it later. And these ones, without having our proper skill, we don't really have any examples that we're going to need to follow. We'll see that later on. And then the sum and difference rule. Sometimes it's called, this process is called linearity. Is that f of x, the derivative d dx of f of x plus or minus g of x. So you have the derivative of sum or a difference. It doesn't even necessarily have to be 2 things. It could be 3 things, 5 things, 2 million things. The derivative of it is f prime of x plus g prime of x. So you can, when you're separated by addition or subtraction, plus or minus, excuse me. Plus or minus g prime of x. Which is to say that to find the derivative of a sum or a difference of things, a bunch of terms separated by addition and subtraction, you just find them separately. Which is nice. Any questions on that? So those are the first 4 rules. The first 4 rules. Basic not meaning easy, but basic meaning the quintessential, the groundwork for which everything else is dependent upon. So we're going to find some derivatives. At first, we are going to show all the nitty-gritty details just because it's the first time we're learning this. However, as we move on, I will stop doing this fairly quickly, actually, because I want you to get to the point with your mental math that you can do these things quickly. And I'll show you some tricks, especially when it comes to part B. So this one, the derivative, sorry, I should have zoomed in. I don't know why I wasn't like that. The derivative of f of x equals 3x to the fourth minus 5x cubed plus x squared minus 2x plus 4. So f prime of x, the constant multiple rule, or the sum and difference rule says that I can just find the derivatives of each one of these things separately. So the derivative of the first term, there's a constant 3 in front, so I can just ignore that. And then find the derivative of x to the fourth. The derivative of x to the fourth by the power rule is 4x to the 4 minus 1. Now you might just see that as 4x cubed, which is what I'd like you to get to. If you saw that right away, awesome. Do that. Don't even worry about it. That is what we're going to start doing fairly soon. Next one, the minus 5, that is a constant that can be brought out front. So minus 5 times the derivative of x cubed, which would be 3x to the 3 minus 1. Plus, for x squared, there's no constant, so we don't have to worry about that. And then it's just going to be the power rule, 2 times x to the 2 minus 1. Then the derivative of 2x, that's the linear rule, which is the power rule, but students kind of want to get a little bit caught up on that. Technically speaking, this would be 2 times 1 times x to the 1 minus 1. That's the power rule in action. But do you remember 0 to the 0, x to the 0 is equal to 1. Anything raised to 0 is 1. Save for 0, but that's another story. Minus 2 and then plus 0. What I would like you to get to fairly soon, because a lot, like we're gonna 2.3, we're gonna learn the next rules. 2.4, we're gonna learn the next rules. So if you don't have this foundation done soon, you're gonna be completely lost when we get to 2.3 and 2.4. So practice this now. Okay, practice this now after studying for the quiz. So this is what I would like you to get to, the point where instead of writing that step, you just write this. That would be 12x cubed minus 15x squared plus 2x minus 2. That is where I would like you to get to. I'd like you to be able to do that in your head. Same thing with the next one, but there's a little bit of an issue. Any questions on that? Isabel, do you have a question? No? Okay. The next one. G of t equals the third root of t plus the fifth root of t squared. There was no radical rule. So how do I do it? There's no radical rule that was mentioned. Write them as exponential form, write them as powers. So just as a reminder, I'm going to write it one more time. This will probably be the last time I write it, is that the nth root of x to the m is equal to x to the m divided by n. The power goes above, the root goes below. Just like in like the saying, there are the powers above us and then roots grow below us. So we're going to rewrite. So g of t is going to equal t to the 1/3 minus, or sorry, plus t to the 2/5. And now we can use the power rule. When you're first, we're gonna write this by first starting out with it, like with all the nitty-gritty details, so I can teach you the trick. But later on, I'm going to skip that. So g prime of t is going to be 1/3 t to the 1/3 minus 1. I'm going to move this down a little bit so I have space to write this. Plus 2/5 times t to the 2/5 minus 1. Now, you can use your calculator for it, but I'm going to teach you the little trick is that when you're subtracting off an integer from a specifically 1, if you're subtracting off an integer, you just write the integer in fractional form. This is the same thing as 3/3, and this is the same thing as 5/5. So it suffices to just subtract the denominator from the numerator to get the new power. So 1 minus 3, that's -2. So g prime of t is 1/3 t to the -2/3 plus 2/5 times t to the -3/5. Any questions on that? So you can definitely use your calculator to do those things, but I'd encourage you to just try to do it without it at first. You'll start to get faster and faster at it. You'll start to improve your mental math skills if you do it that way. It might take a little bit of time at first, but you'll get better at it. Start to notice the pattern. Next thing, and this one is important. Find the derivative of the following functions. H of z is equal to the parentheses z squared minus 3z plus 1 times in parentheses z squared minus 1. As a note, very important note, d dx of f of x times g of x is not equal to f prime of x times g prime of x. It's not true. The derivative of a product, unlike limits, right? The limit of a product was the product of the limits. We could just break it into 2 different limits. That's not true with derivatives. Sadly, derivatives don't follow that rule. Derivatives have a little more complications than that. And we'll talk about that in 2.3. But this one, so we've got to FOIL first. So h of z, if we FOIL this out, you got to make the sound too. So that's just making it confusing for me, actually. I regret that. Z to the 5th minus z squared minus 3z to the 4th plus 3z plus z cubed minus 1. So I'm going to rewrite that in descending order. It's not required because all those terms are different powers, so you don't need to worry about combining like terms here, but I'm still going to do it. So h of z is z to the 5th minus 3z to the 4th plus z cubed minus z squared plus 3z minus 1. And so now, starting now, I'm going to stop writing out as much detail, and I'm just going to write the answer. This is what I'd like you to get to. I'd like you to be able to look at this and say h prime of z would be 5z to the 4th minus 12z cubed plus 3z squared minus 2z plus 3, and then technically minus 0, but that doesn't do anything. Any questions on that? Yes.
The power rule.
For all those terms, yes, I use the power rule. I guess technically speaking, for the last 2 terms, I use the linear term, the linear rule, and the constant rule. But the funny thing is, the linear and the constant rule can actually be proven by the power rule. And the reason for that, so check this out. The derivative, you can prove it real quick you don't need to write this down. This is just for observation. The derivative of a constant, that would be d dx. Would you also agree with this? Pretty much. Because x to the 0 is 1. And so by the power rule and the constant rule together, that would be c times 0 times x to the 0 minus 1. And that would just go away and be 0. So that's another way to prove it. A little hand wavy, but whatever. So similarly, with part B, the derivative of a quotient is not equal to the quotient of the derivatives. So note d dx of f of x divided by g of x is not equal to f prime of x divided by g prime of x. Sadly, there is a different rule for it. It doesn't work like limits. So derivatives aren't as nice. So we have to simplify first. But that's not too hard because you're dividing by a monomial. So you're just going to divide each term by the monomial. So f of x equals x cubed divided by x minus 2x to the 1/2 divided by x. So f of x is equal to x squared minus 2x to the negative 1/2. Because you'll do 1/2 minus 1, that'll give you negative 1/2. So the derivative then, f prime of x is equal to 2x to the first power plus x to the negative 3/2. Take a second to make sure you digest why that's true. Make sure you understand the algebra that went in there. Algebra and arithmetic, rather. A little bit of algebra, a little bit of arithmetic. I will explain it in just a moment, but I want you to make sure you're trying to figure it out. So hopefully the x squared turning into 2x when you take the derivative is not is apparent. But this one, you're going to have negative 2 times negative 1/2. That's why it's plus now and just a plus 1 because the 2 and the 1/2 cancel. And then negative 1/2 minus 1, that would be negative 3/2. So I'll write that down if you want to include this. You don't need to if you don't. If you see it already, awesome. If you don't see it, it's because it's negative 1/2 minus 1, which is the same thing as negative 1/2 minus 2/2, which is negative 3/2. That's the reason why that works. Last one that we have here. Then what do we move on to? Yes, some other important ones. Last one here. We're going to rewrite the 1 over w to the pi as exponential form because we don't have a rule for that yet. So we're just going to rewrite it in exponential form. So that would be w to the 7/3 plus w to the negative pi. So p prime of w is equal to 7/3 w to the 7/3 minus 3/3. That would be 4/3. And the reason why I'm saying 7/3 minus 3/3 is become subtracting 1, which is the same thing as 3/3. And then minus pi times w to the negative pi minus 1. And just like with that square root 2, pi is an irrational number, so we cannot combine pi and negative 1. So we have to just leave it as is. It's not all that bad, though. Any questions on that? Okay. So then we have some more rules. These are the other basic rules. These ones, and then you might wonder, Well, the basic rules, so we've covered polynomials essentially with the first section. And now we're covering exponentials and logarithms. There are a couple functions that we don't have up here. 6 of them in particular. Sine, cosine, tangent, cotangent, and everything like that. Why aren't those listed? And the reason for that is that in order to find the derivatives of tangent, cotangent, cosecant, and secant, you need to know a little bit more. We need to go to 2.3 for that. So the derivative of e to the x is very, very simple. It's e to the x. There are only 2 functions that do that whose derivative is itself. The derivative of 0 is 0 because it's a constant. So that is the only function that when you take its derivative, it gets back itself, and e. Very, very fascinating concept about e. Super cool. So the derivative of an exponential function is itself. When you have a to the x, it's going to be natural log of a times a to the x. So when you have the derivative of a non-x, like a non-e base, so no, like not the natural base, it's ln of a times a to the x. The derivative of natural log of x is 1 over x. And the derivative of log base b for any other logarithm other than the natural logarithm is 1 over ln of b times 1 over x. What I will tell you is that, note, you don't need to memorize parts B and D. A and C, yes. And I wish I try to avoid making you memorize things wherever possible, but sadly, those are ones that just need to be memorized. But B and D, I don't need you to memorize them. I feel like that's an unnecessary thing. And the reason for that, by the way, the reason why I argue that is that every logarithm by the change of base theorem, if you remember that, did you guys go over the change of base theorem in 126? It's okay if you don't remember it, but basically the change of base theorem tells you that you can convert any logarithm into a natural logarithm. So why bother learning anything else besides just the natural logarithm? And then a to the x, any exponential function can be rewritten as a natural base. It's just a fact, which is pretty cool. You can rewrite. So the reason why this works, by the way, the reason why is that a to the x, you don't need to write this down, but this is just a fun fact. This is equal to e to the ln of a to the of a times x. That's true fact. Pretty nifty. The e and the ln cancel, and you're just left with an a. Like, just a nifty little trick. And the change of base theorem is how you convert this into this. But so that's being said, you do not need to have B and D memorized. If I ever ask a question on an exam that includes those ones, you will be provided that derivative. E and natural log, though, those need to be memorized. So this one right here, find the derivatives of the following functions. So just to save myself some frustration later, I'm going to rewrite this in exponential form right off the bat. That's the 7 times the 5th root of x. Speaking of which, just when it comes to exam time, please feel free to ask. That is the 5th root. This is not 75 times the square root of x. Don't break my heart, okay? It hurts when students accidentally make that mistake. That, like, you can always ask for clarification here. Like, if on an exam is like, is that 7 times the 5th root, or is that 75 square root? Anyways, so y prime or dy dx, however you want to write it, the derivative of e is itself. The derivative of 2x cubed, that would be plus 6x squared minus the derivative of 7x to the 1/5. That'd be 7 times 1/5, so 7/5 times x to the, take a second, try and get the fraction right. 1/5 minus 1 would be -4/5. And then the last piece, that's a natural log with a base of 7. So that's part D, which is provided for us here, and it would be provided on an exam or a quiz if needed, which would be plus 1 over natural log of 7 times 1 over x. You could write that as 1 over x times natural log of 7. I just find this to make it, for it to make more sense in that fashion. That is our derivative. Similarly for this one, g prime of x, the constant 3 is ignored. The derivative of natural log is 1 over x. So this is 3 over x. That's a different base than the natural base for that 21 to the x. So it's going to be minus ln of 21 times 21 to the x. And then the derivative of 5 is 0. So we don't need to worry about it. The derivative of 5 is 0 because it's a constant. Any questions so far? Way faster, by the way, than doing this by the definition. Am I right? Could you imagine if I asked on a quiz what the derivative of this function was? You'd have to FOIL out z plus h to the 5th, z plus h to the 4th, z plus h cubed, z plus h squared, and z plus h. You'd have to do all that. Do you want to do that? I mean, I can put that on the quiz. You just want me to do that? I'm seeing a bunch of shaking heads. Yes. Okay, perfect. We'll put that one on the quiz. Kidding. That'd be awful. Okay. Now let's find some application problems, some more tricky ones. Determine the values of x for which the function h of x equals 2x cubed minus 1/2 x squared minus 15x plus 3 has a horizontal tangent line. What do I do? Never seen it before. Horizontal tangent line. That's right. Estrom is absolutely correct. So a horizontal tangent line, let me underline that. A horizontal tangent line would mean that m sub tan would equal 0. But that's the derivative. So what this question is really asking, if we really decipher it, if we think about this in a calculus concept, is we're finding the x values for which the derivative equals 0. So we need x values that make f prime of x equal to 0. That's what the question is asking us. Inadvertent. Or rather, what it is saying without saying. So we need to find the x values that make the derivative equal to 0. In order to find the values that make the derivative equal to 0, we need to have the derivative. So that's what we'll find first. So h prime of x is, I want you guys to find it. I will slowly fill it in. I want you to practice yourself. Derivative is first term 6x squared. Second term minus x. Third term minus 15. And then the plus 3's derivative would be 0. Big old goose egg. The derivative of a constant is 0. So h prime of x equaling 0 that would tell me that 6x squared minus x minus 15 is equal to 0. And that factors. So, I mean, you could, since we're just being asked to find the values for which it's 0, you could use the quadratic formula if you really want to. It's not wrong to do so. But this one does factor pretty nicely, if I remember correctly. Not going to be 6 and it's not going to be 6 and 1, so it has to be 3x and a 2x. See here, 3 times 3 give me 9 and 5. Yeah, okay, 5 and 3 plus minus. All right, so we get negative 10x plus 9x. That gives me negative x. Good. By the way, just in case you're curious, I got really because that was the only way I was taught. I got really good at doing the guess and check. That's why I was able to do that quickly. You don't have to do the guess and check method. It's very, very bad in most cases. So, but you can also use the quadratic formula. Once again, you don't have to find it by factoring. You can use the quadratic formula. But this means that x equals, setting it equal to 0, x equals 5/3 and negative 3/2. And since the question was only asking for the x values, we're all done. If it had asked for the points, then you'd have to plug those x values into the original function to find the corresponding y value. Oh, my favorite types of questions. Find the equation of the line tangent to the curve fx is 3x squared and perpendicular to the line 3x plus 18y equals negative 7. All right. When you've encountered a problem that you do not like, that you have never seen before, let me make sure how much time we have left. Okay, perfect. We're mostly on time. We're getting caught up. Perfect. So find the equation of a tangent line to the curve f of x equals 3x squared that is perpendicular to the line 3x plus 18y is equal to negative 7. Okay. Whenever you encounter a problem, take a deep breath that you've never seen before. Take a deep breath. Say what you know. Start listing off things that you know, because those things can help you. Maybe it helps you, maybe it doesn't. If I want to find the equation of a tangent line, I need a slope and I need a point, right? So we need, if I need slope and point on f. Not on f prime. That's not like this. These are tangent lines to f, not to f prime. So we need a point on f and we need the slope. So in order to find the slope of a tangent line, you need to find the derivative. But it's perpendicular to the line 3x plus 18y is equal to negative 7. So we need to know, we need our tangent line to be perpendicular to that line. What's the slope like? So if we find the slope of that line, we can take the negative reciprocal to get the perpendicular slope. So what's the slope of that line? Well, it's in what we call general form right now. We need it in slope-intercept form. Convert to slope-intercept to find its slope. So 3x plus 18y equals negative 7. That gives us y is equal to, subtract the 3x, negative 1/6 x minus 7/18. Yeah, the 7/18 is scary, quote unquote, but that's not anything we're interested in. Because we're only interested in the slope. Since, and I'm going to underline that. So m perp equals negative 1/6. The slope of the line perpendicular to our tangent line has a slope of negative 1/6. That means that m sub tan will equal negative 1 over negative 1/6, the negative reciprocal, or positive 6. That's if you want to do the math for it. Take -1 and divide it by the original slope to get the perpendicular, or you could just flip the fraction, change the sign. That's the quicker way. Flip the fraction, change the sign. Flip it, you get 6, change the sign, positive 6. However you want to find the perpendicular slope, that's fine. That's MTAN. So in order to find, here's the thing. Look at this problem. We just found what the slope of the tangent line is. So we already have the slope. We still need the point. How do I find them? They didn't say at x equals blah. If I set the derivative equal to the slope of the tangent line, I would be able to solve for x. So f prime of x is equal to 6. Like f prime of x is equal to 6x. So from the blue, we need 6x to equal 6. That allows me to find an x value. That tells me that we get a slope of 6 when we solve that equation. That gives us x equals 1. And that allows me, now I know where a tangent line will have a slope of 6, and that will allow me to find the corresponding point. Now we can find the point on F by plugging in that x value. That's a tricky problem. That's a tricky problem, but a good one. A very, very good one. Because yes, we've already found the MTAN, but we also can use it to find the x value. So f of 1 is 3 times 1 squared. And once again, I'm doing that for our notes. You don't need to do that on an exam or on a quiz. I'm doing that to remind us that we're plugging it into the original function. I'm showing me plugging it in by doing 3 times 1 squared and not just writing 3. So we understand that I used the original function to find this y value. I didn't use the derivative because that would give me a wrong answer. So we get the point, which is equal to 3. So we get the point 1, 3. So we have MTAN equals 6. We have the point. So the derivative, the tangent line will be y minus y sub 1. So y minus 3 is equal to m, which is 6, times x minus x sub 1, which would be 1. Or if you really want to go the extra mile, that's 6x minus 6 plus 3, that's minus 3. However you want to do it is fine with me. Okay. We only have less than a minute left, and I want to, like, with that last little bit, I want to tell you why I like point slope form over slope intercept form. Because when you look at it in slope intercept form, you don't know where it's meeting the curve. You don't know where it's meeting the curve. Whereas with point slope form, it's saying you know where the tangent line has a slope of 6, it's at 3, 1. That's the great thing about it. We'll come back next time and we'll do this problem. This problem is awesome, incredibly difficult. That's why there's a whole page, but it's a really, really fun problem that stretches your learning. So we'll come back with that one on Thursday and then go into 2.3. If you have any questions, feel free to send me an email or come to my office hours. Your exams will be handed back on Wednesday, and you have a quiz on Wednesday on 2.1 only, just 2.1, nothing on 2.2. All right, guys. Have a great rest of your day, and I'll see you on Wednesday.